Kind of an easy lesson for today.
Yay.
We are going to get to logarithms soon, okay? It's actually our third lesson of this chapter. But there's a couple things I'm going to talk to you first to make the log stuff make sense, okay? So first thing we're going to talk about are inverse functions. Our objectives, we're going to identify one-to-one functions. We've talked about that, but we're going to go more in depth. Determine whether two functions are inverses, and then find inverses of functions. Okay, so that's what we're going to try and cover. What I have here, you don't need to write this down. These are conversions to go from euros to dollars. Okay, these are these two functions that gives you this. So the first one, if you plug in American dollars times by 0.8, you get the number of euros it's going to be. And I think I have the number, the official number written down. Let me see. It's not exactly 0.8, it's 0.8498 is what it is. So I rounded, I just said 0.85, or well, just 0.8 I guess. But anyway, here's a little XY table with it. So if you get $100, it's 80 euros. Okay, $150 is 120 euros, so forth. This over here is converting to US dollars. So if you give me the euros, I can tell you the number of dollars you're gonna get. So $80 is 100. 80 euros is $100, 120 is $150, 160 is 200, and so forth. Now, if you look at the tables, what do you notice about these two XY tables?
Opposite.
They're complete opposites, huh? They literally just flipped everything. If you were to graph it, okay, the graph looks like this. It's a very rough sketch, but just to give you an idea, okay? These guys are reflected across the line y equals x, okay? Both of these are characteristics of inverse functions, okay? So inverse functions literally take your xy points and flip them. That's what the inverse function is going to look like, okay? So these are the characteristics we're going to try and observe throughout this lesson. Make sense? So let's talk about inverses. Quick little definition. First, let's talk about one-to-one. A function f is a one-to-one, and there are dashes in between that when you write it. I'm going to cheat it and start doing this instead, one-to-one, okay, just for abbreviation. If for a number a and a number b in the domain of f, if a doesn't equal to b, then f of a does not equal to f of b, or equivalently, if f of a equals f of b, then a must have equal to b. Okay? Now, sounds like a lot of gibberish. Let me try and decipher this for you a little bit. Okay? Remember what a function is. Okay, a function has an input with an output, right? They're connected. Well, a one-to-one, if you recall, is when a function has outputs that are unique, right? The output only gets picked once. So, for instance, if I had this is not the greatest example, 1, 2, 3, 4, 5, 6, but oh well. Notice that 2, 4, and 6 are unique, right? They only get picked once. That's like a one-to-one function, okay? Now what this is telling you up here is this. If they're not equal, if they're not the same x value, then the outputs can't be the same. Okay, so for instance, okay, I don't want to write this. Well, let me rewrite this part and then we'll change some things. So let's change this to a, I don't know, 7, and let's change that to a 2, okay? So if you notice, okay, 7 and 1 both get graphed to 2, right? Okay, so that's not a one-to-one function already. So 2 is not being unique, okay? But notice, were the x values the same at all to give you that? No. And that's what this is talking about here. The only way these two can be the exact same is if these guys have to be the exact same. That's it. Okay, so for instance, if you had a function like this, y equals 2x plus 1, okay? What number can I plug into here that when I simplify it gives me a 5? 2, right? Now, can any other number give me that 5 besides 2? No, that's it, right? So that's what this is saying. Only a 2 can do that, all right? So if A is 2, then B has to be 2 to give me an output of 5. So that's what a one-to-one is talking about there. Okay? Any questions on that definition? One state? Now remember with graphing, if it didn't pass the vertical line test, it wasn't a function, right? Okay? So we have another test graphically to determine if it's one-to-one. So let's talk about that test. So here we go. We call it the horizontal, make sure I spell this right, horizontal line test. A function defined by y equals f of x is a one-to-one function if no horizontal line intersects the graph in more than one point. And I'm going to give you an example right underneath it. So we call it the horizontal line test. If it crosses the function in more than one spot, it can't be one-to-one. Visually, it's pretty easy to see. So right here, it did cross it twice. See how -1 and 1 are both paired to 2, right? So no bueno, 2 is not unique. So this is not a one-to-one function, okay? Easy to see, huh? Now, any questions on that? So far, so good? Okay, now why do we need a one-to-one? We'll talk about that just a little bit later, but these are important when we talk about inverses. So let's just try an example. So determine whether a function is one-to-one. No question mark there. And I'm just going to give you a set of points. I'm going to give you a relation here. Oh heck, I'll spoil it. I'll give you 2 of them. I got 2 relations. So the first one is function f. Those are the points that are involved with it. And then the second example, you got function h, and those are the points that are involved with it. So looking at function f, any thoughts? Is it one-to-one?
No.
Nope. What number is being picked twice?
0.
0. That one and that one. So, nope. Very math official term. Nope. So, not one-to-one. Okay, let's look at example B. Is that one-to-one? Absolutely. There's only 1, 4 as a range value, 1, 5, and 1, 6. There you go. It's one of those things, if you ever look at your notebook like months down the road, it's kind of fun to do stuff like this. You look back and like, why did I do that? Why was I so excited? Just because. That's all. Okay, so any questions on this? Easy to spot, right? Just look for the duplicate y values. Still keep in mind that you have to look at your x values too. Make sure there's no duplicates there, because if there is, then it's not a function, right? So we don't want to forget that part either. All right, let's practice horizontal line test. So use the HL test to determine if the graph defines y as a one-to-one function. Okay, this is going to be the hardest examples you ever encounter. Be prepared to start sweating here. I feel bad giving you these hard problems, but someone has to do it. I got tissues, don't worry. Okay, let's take a look at part A. Is that one-to-one?
Mm-hmm. No,
No, it's not.
I wasn't looking at the graph, I'm sorry. Geez, these questions really are hard.
Okay. See, I told you these were hard. So yeah, it's twice. So whatever that number is not unique, right? If that y value is 5, 5 is not unique. Okay, part B, is it one-to-one?
No. Wait.
Justin's on a roll. Answer is C, it is. So I'll put here, not one-to-one, and this is yes, one-to-one. Okay, no matter where I draw the horizontal line, it only hit once. See, I thought I was kidding with that. Huh. All right, questions? So far, so good? Okay. Now, let's use some algebra to figure out if something's one-to-one. So this is easy. If I give you relations, that's no big deal. If I give you graphs, it's no big deal. What if I just give you the equations, right? How can you use the equations to figure out if it's one-to-one? Okay, so let's try that next. So example is the right color. Okay, so use the definition of a one-to-one function to determine whether a function is one-to-one. Now, by the way, could you just graph them anyway? Just use the HL test? You could. But if you don't have a graphing calculator on standby, it's good to know how to do this anyway, right? Because our functions could look simple, they could look complicated. Now for part A, that's a line, right? So I already know what the answer is going to be. It's going to work out. So hopefully when we're done with the algebra, it agrees, and it should. So here's how you figure it out. Let's look at the definition over here. I'm going to use this fact right here. Okay? That's what I'm going to use. Could I use this fact up here? If they're not the same and the y values are not the same? Yes. But that's a little bit more difficult to use. And you'll see why after we're done with this example. So I'm going to use this. This is equivalent. Okay? So what I'm going to do is I'm going to look at part A and say, hey, if the y values are the same, the only way that can happen is that the x values had to be the same. Okay? And if that's true, it's one-to-one. So let's go ahead and do this. I'm going to write down the wordage that you want to state with this. So I'm going to say here, we must show if f of A equals f of B, then A has to be B. Okay? So let's go ahead, we're gonna assume that the y values are the same for these two x values, which are a and b. We're gonna assume that they are equal. We're gonna work backwards to see if you look at the definition, if a is equal to b, okay? So let's plug a into here. So it'll be negative a half a plus 4. Now what's f of b? We'll plug b into there. So it'll be negative a half b plus 4. Sorry, that a should be on the outside. There we go. From this step, you simplify. And we're hoping that when we're done simplifying this, we get an a equals b. Okay? If we don't, then it's not 1 to 1. That's no big deal. Immediately, I can see that the 4's cancel, right? They're gone. So I get negative a half a equals negative a half b. Now you could probably stop there and say they are equal, but anytime you're trying to prove something and you're using a definition, you better make sure you follow it to a T. So you want this to show. So what I would do next is multiply both sides by -2 to get rid of the half. So multiply by -2, multiply by -2, and then I just get a equals b. Awesome. So this is a 1-to-1 function. So let's go ahead and write a little conclusion statement, because this is English class apparently. Since f of a equals f of b implicates, that's a nice word, a equals b, then f is 1-to-1. Okay? Now, before I go to part B, let me explain again what we just found, okay? Because I think a lot of times we have so many variables in here, we kind of lose sight as to why we even did this in the first place, okay? What we just told the reader, that if the y coordinates are the same, the only way that happens is if the x coordinates are the same, right? You don't have a situation like this, because remember, this isn't 1-to-1. So the only way it can be 1-to-1 is if it's only this part. If I just had that part of the grid, okay? 1 is the only way I can get an output of 2. That's it. If it didn't, then you're telling me there's 2 different inputs that gives me 2. It's not 1-to-1 anymore, okay? Questions before I move to part B? Part B. Okay. So again, I'm going to assume that the y values are the same for a and b. So let's go ahead and plug them in. So this is 1 over a squared minus 2, 1 over b squared minus 2. Apparently I flipped colors again. I was supposed to do all blue. Oh well. It is what it is. So immediately I could see that what? The -2's are going to cancel out, right? So those are gone. I get 1 over a squared equals 1 over b squared. So here's what I'm going to do. I'm going to multiply both sides by a squared b squared to get rid of the fractions. Okay? So we're going to multiply this by a squared b squared, a squared b squared. That way we're back to normal. So a squareds cancel out here. I'm just left with b squared. B squareds cancel out here. I'm left with a squared. Now, because this seems very picky, but you see how a is listed first in definition? I'm going to flip them. Again, it's not really that ridiculous. When you look at a proof paper or anything, you want it to be identical to what you're looking at. Okay, that's all it is. So for my last step, well, let's think about it. If I take the square root, I get plus or minus b. Okay, that's not the same thing as them equaling each other. Now, why is that? Let's think of an example here. The first one. It's like I left it up here on purpose. Okay? If I square a -1 and a 1, if this was a and this was b, were they equal at the beginning? Were they the same number? No, but they did give me the same output. They did. That's why this is not a 1-to-1. Okay? Okay. Even though up here you're like, oh, they are the same, but that could be a 1, that could be a -1, right? So So the square is kind of misleading there. That's why I took the square root, so we could see that process. So unfortunately for this case, and let me just write this down properly, okay? So f of a equals, f of b does not necessarily imply a equals b, therefore f is not 1 to 1, okay? So yeah, this did not work. Again, the only reason why I took an extra step is to kind of flush it out over there so you can kind of see that. Stretching?
No, I'm asking
Question.
a question. Yeah.
Yeah.
Would it not be positive or positive negative A equals positive negative B? I mean, it would still be like.
Well, you can
still
only
be 1 to 1,
you can only do
but-
square root to one side. You're not gonna be able to square both sides like that. If you're solving for one of them to see if they're equal to each other, one of them's gonna have the plus or minus there.
Okay,
So,
because
again, if
Yeah.
you were to graph this, actually graph it, you would see that there's gonna be a situation like this,
yeah, I just
no matter what.
I thought because like since they both have a square on them, you take the square root of both sides, they both have positive and negative,
Mhm.
but I guess no.
Not something you want to do there. No.
Okay.
But good question, though. Very good question. All right. I think we're doing good. So let's bring inverses into it. So now we talked about one-to-one for a bit, for a good reason, because we need them for inverses. So let's talk about that definition. Oh, this looks great. The erasing of this board was brought to you by Amazon Erasers. They're garbage. Okay, definition. Let f be a one-to-one function. Okay. Then g is the inverse, so that's important, we'll underline it, of f if the following conditions are both, another keyword, true. So here's the conditions. 1, f of g of x equals x for all x in function g. 2, f of g, I'm sorry, I gotta flip those. A little too fast there. G of f of x equals x for all x in f. I'm gonna draw some pictures for you to explain this a little bit more, or at least to flush it out a little bit, okay? Not to say the definition's bad. This is exactly what we're gonna be using for the next examples. But what does that mean? Let's talk about inverse operations. What's the opposite of addition? Subtraction. Okay, opposite of multiplication? Division. They undo each other, right? What we're trying to do is we're trying to figure out what function can undo it. So what equation can undo another equation? Now, why do we even want those? Let me draw some pictures. Let's say these are my domain values. Those are my x's, right? All the x's. I'm gonna plug them into function f. And then my output are my range, right? I'm gonna get all that just all the way over there. And the key part here is it has to be a one-to-one. I'll explain a little bit why that's important. So I take some domain, some x value, I plug it into f, and I get some output value. What if I want to know what I started with? What if I went from here and I want to go to here, right? So I got to go backwards. So I got to find some equation that undoes all the operations here and tells me what did I start with, okay? So this goes into an inverse function, we'll call it g, and it will give you what you started with, okay? That's what inverses do. So this, whatever this is, you're gonna plug it into here. It undoes all of F's stuff. And then you start with, or it gives you what you started with, okay? Questions on that? Now, why does it have to be one-to-one? Well, one-to-one means that one input for a unique output, right? So let me do this. Okay? If it wasn't one-to-one, let's say this x and this x value, I plug them in to function f, and they both give me that output, right? Well, if I plug this into my inverse, which x value is it going to go to? I don't know. I cannot come up with a function to undo everything and give me both inputs. Can't do it. So that's why this is important, okay? Because now I know there's only one input for that output, not multiple, to where I can't figure out what the end result is. Any questions on the importance of one-to-one and what inverses do? Okay. Well, let's move on. We're just going to continue it. This erasing of the board was brought to you by Amazon Erasers. This is also an Amazon eraser. It's not working too well. Oh well. We're going to make do with it. Now let me teach you about notation a little bit. Oh, come on, really? Seriously? So notation. Okay. So for a given function f, we often denote its inverse as f to the negative 1 power, okay? So if you see that notation with a function symbol, we're talking about its inverse, okay? That's why I didn't put it over there. I just said g was the inverse, but now we're gonna introduce the symbol. So instead of using g, I'm gonna use f to the negative 1. So given a function f and its inverse f to the negative 1, the definition implies that f of negative 1 of x gives me x. So in other words, this undoes f and you get what you started with. That's what the first picture that I drew over there for you. And here's the good news. It doesn't matter the order. You could flip the two functions together and you're still going to get x. Because remember, it's one-to-one, right? It doesn't matter if I take the inverse and plug it into the function or change the order of it. I'm still going to be able to find what I started with, which is great. So order doesn't matter with it. So we call those guys unique. Okay. So let's do some examples with it. So for this example, okay, determine whether the functions are inverses. So there's the first one. I'll put the other one over here. Important. We're going to test this out. We're We're going to plug one function into the other and see if we get x as an answer. X has to be an answer because x is the input value, right? And if both of these work, they're inverses. If one of them fails, guess what? Don't even test the other one. Don't even go any further. You're done, okay? Because they both have to be true. So let's look at the first guy. This looks like fun. So let's find f of g of x. Okay. I mean, I should probably put this. Okay, so just using the symbols like this, composition implies this. So I'll write that out fully. So let's plug g into f. See what we get. Okay. So it's the fifth root. Now, x I'm going to take out, right? Let me just underline that. So this, well, I'm going to box it. I'm going to take this and put it right in its place, right? The whole thing. And simplify. And we're hoping that when we're done simplifying, we just get an x. So we get negative, and then in parentheses, negative x plus 2 to the fifth power plus 3. Not looking promising. So if I simplify it, I get the fifth root. Now these two negatives will cancel out. So you just get x plus 2 to the fifth plus 3. Now, if I were to, and I'm not, but if I raise that to the fifth power and take the fifth root of everything, is it going to come out nice at all? No. Are you just going to get an x afterwards? No. So guess what? Nope. So they are not inverses. Okay? You don't, I'll put this here. It doesn't equal x. Okay? That's why we can't go further with it. And please don't raise it to the fifth power. Like when you practice this yourself, be smart about it. Okay? Think about it. To the fifth power, you're going to have a lot of numbers in there. And not everything's going to reduce and simplify to just an x at the end. Now part B, you're probably thinking, well, if that didn't work, this must work. And you'd be right. This won't work, okay? But let's see it in action now. Not to spoil the fun for you. Okay. So I'm now ready to use the wrong color, blue. So I'm just gonna jump right to the f of g of x part. So anywhere I see an x, this whole thing goes into it. Now this is gonna be a fraction over a fraction. So we're just going to take our time simplifying it to make sure we understand. So this is going to be 4 over this whole thing. So 4 over x minus 2, and the outside you're going to get a plus 2. Okay? Looks ugly, but it's going to simplify really quickly. Now I'm going to show you what's going on behind the scenes, and then in the future I'm just going to kind of shortcut it a little bit. So this guy right there, let me rewrite that. That's like 4 divided by 4 over x minus 2, right? That's what it's saying. But when you learn division, you multiplied, and then you did the reciprocal, right? That's how you were taught. So what happens to the 4's then? They're gone. We just have an x minus 2, huh? So this whole thing is just x minus 2. Okay? So this is a side note. It's what's going on behind the curtain. So this is just equals x minus 2 plus 2. 2's cancel. We get an x. Can't cheer yet because we still got to test the other side, but at least we know that that one works. Okay? So let's do the other one. So let's do g of f of x. So I'm going in the reverse direction. Let me just erase this blue box. So now this whole thing is going to be replaced to that guy. Okay? So I get 4 over x plus 2 minus 2. Now we lucked out again, huh? Look what happens. These 2's are gone, huh? Boom. Finished. So we just have 4 over 4 over x. Okay, because those are going to cancel out. So what does that reduce to? X. Going based off of what I did here, right? These 4's are going to cancel. Same thing, these 4's will cancel. But until you get familiar with it, if that's still not working with you, I mean, you can do this off to the side, right? Try and convince yourself. All right, we got success. That's awesome. So therefore, okay, well, let me just put a little description. So since f of g of x equals g of f of x, which equals x, okay, f and g are inverses. Alright. Any questions on that? Pretty easy to figure out, huh? You're just plugging one into another. I think a lot of times we're like, why are we learning composition? This is one of those reasons why we learn composition of functions. There's others, but that's one big one. Okay, so now we gotta what? Find an inverse to wrap things up. So what if I gave you a function, I said, hey, find its inverse? How do we do that? I'm so glad you asked, let me tell you. Put up here, procedure. To find an equation of an inverse of a function. Okay. Oh, and let me just put this here too. Okay. We already talked why, but must be a one-to-one function, right? So just keep that in mind, okay? See, it was so important I used 2 different symbols. But hey, it's that important. One-to-one function. If it's not a one-to-one function, you can't find its inverse, so don't do it, okay? No matter how badly you want to, just can't do it. First step, replace f of x by y. We know they mean the same thing because it's just a symbol, but you want to go ahead and do that first. Second step, interchange x and y. Third step, you're going to solve for y. And then you're going to make it look like an inverse, so replace y with the symbol for an inverse. Okay? Make it look nice and pretty. Now, look at step 2. Why am I interchanging the x and y to find an inverse, right? Let's go back to my example at the very beginning of class. These are inverses. What happened to the x and y's for both tables? They flipped, right? So that's what I'm doing. If I flip the x and y in the equation and solve for y, I'm coming up with the inverse equation, okay? So visually and by table, we can see y's importance. Interchange x and y. Okay, so let's try it out. Write an equation for the inverse of a function, which we're going to say f of x equals negative x cubed plus 3. Okay. All right, let's follow the steps. So we're going to replace that with a y. So f of x just is now a y. And then we're going to exchange their positions. So x is over here, y is over there. Next step, solve for y. Alright, let's do that. So I'll subtract 3. Just like that. Divide by -1. Or multiply by -1, does the same thing. So this would be -x plus 3 equals y cubed. And then our last step is to what? Take the cubic root. So we have the cubic root of -x plus 3 equals y. And then just like step 4 said, you gotta make it look like it. So this will be our inverse function. So we'll change y out and put the actual symbol in its place. But there we go. This function will undo this guy and give me the x value I started with. Don't believe me? Let's check it. So we're just gonna do it just for this problem, but let's check. Alright, so I'm gonna go ahead and check the forward implication. So plug in the inverse of the function, and I should get x when I'm done. Okay. So let's see what that's going to look like. So this guy goes in for x. So negative, okay, cubic root of -x plus 3. That's being raised to the 3rd power plus 3. It always looks ugly when you first substitute it, but doesn't necessarily mean the rest of it's going to be ugly. If you're cubing a cube root, doesn't that just get rid of the sign? So you just get negative, and then it's going to be -x plus 3 plus 3. And I think we're done, huh? So this would make it a positive x. This would be a -3 plus 3 is 0. That's looking pretty promising. So let's go and reverse it and see if we can't get the same thing. So now we're going to take my function and plug it into the inverse. And hopefully we get the same thing. We get x. Okay? So let's try it out. So now I'm going to plug this into here. So I get the cubic root of negative, and then -x cubed plus 3, and then plus 3. Just like the other one, looks kind of ugly, but when we simplify things, it's not going to be bad. So we get the cubic root of x cubed minus 3 plus 3. I went ahead and just distributed the negative to both terms. And I think we're done again. These are going to cancel out to 0, and the cubic root of x cubed is just x. So hey, we did it right. That's awesome. Any questions? Yes?
So we check inverses like this, but
Mhm.
my question is, why can't we just multiply an inverse and a standard function like together and get 1 equals 1 to check?
Well, if I multiply this with this, I'm not going to get 1. Not going to work.
So when does the inverse property work when it does equal 1? Because it's, you know, if I multiply 1/2 and 2, I get 1.
Mhm.
But it doesn't work for like
Well-
equations like this.
Well, think about it. Multiplying is not the same as inputting it into the other function. Because essentially, and I'm going to draw it up here, it's undoing the operations. So let me show you this. So looking at this example here, let's look at a visual. So here's my domain of f, okay? And here's my range of f. Now think about, look at just the top equation. Okay, so what is it doing? We're not going to worry about the negative because that's not going to affect it. So first, you're going to cube it, and then add 3. Right? That's what you're doing for everything.
Yeah.
Okay. Now, to go in the reverse direction, you're going to subtract 3, then take the cubic root. Get you back to the original. So that's why we don't multiply it. We put them inside of each other to undo those operations.
I think I get it because 1 and, or x and 1 over x
Mhm.
they multiply to equal 1, but they're not inverses because they don't, like, the y value isn't going to equal the x value, and the x values aren't going to equal the y value. Okay.
So any questions on the visual there? Does that make sense? So you're just undoing things, right? Okay. Okay, let's see. I think we should have time for one more. Well, I'll tell you what, yeah, we got time for two more. Wrap things up. Okay, example. Write the inverse for the one-to-one function. So f of x equals negative 2x plus 4 over negative x plus 1. We're going to do the same procedure, but this has a fraction to it. And I want to at least give you a good step-by-step on how to mess with this, okay? It's not anything tricky, but it's just good to know what you're getting into. Again, I'm going to replace it with a y. So negative 2x plus 4 over negative x plus 1. And then interswitch them. So x is equal to negative 2y plus 4 over negative y plus 1. Now we're going to solve, huh? Well, it's going to look, not ugly, but it's going to look a little bit more complicated at first, but then we're going to simplify it nicely. So I'm going to go ahead and multiply both sides by negative y plus 1. Kind of out of space there, so I'm going to move it up here. So multiplying, we get negative xy plus x on that side. On the other side, those cancel. I get negative 2y plus 4. Now the goal is to solve for y. What I would recommend is get any term that has y's to one side. So I'm going to add this 2y over here, and then I'm going to subtract the x over here in one step. Again, the goal, get the y terms to this side, everything else the other side. So this is going to be 2x minus xy equals, and this will just be 4 minus x. We okay with what I did? So again, I just moved this over by adding. Oh, not x. My gosh. Now I understand why people look confused. Add the 2y over, and then I just subtracted x over here in one move. Okay, now these both have a y in common, right? I can factor it out. Now, the y can be by itself, huh? It's a little bit easier to work with. So my last step is to divide by this guy. Okay, so I'll show that over here. So I'm going to divide by 2 over x. So those are gone. So I just get y equals 4 minus x over 2 minus x. And then, of course, we're going to make it look like it. So use the inverse symbol. And we are good. I'm not going to check it. I'm going to save time with us. But if you really want to know, you can plug this back into each other. Last example. This is good. There are times when we have to restrict the domain to make it a one-to-one. So for instance, what if I had a problem? Okay, that's not a one-to-one, right? So I can't find an inverse for it. But let's say I tell the reader, hey, let's only consider when x is 0 and bigger than that. Can I find an inverse for that now? I can. Okay, so let's just give you one example with restricting a domain, okay? So f of x equals 4x squared minus 4. And again, I'm going to restrict it, so only when x is greater than or equal to 0. That way I can make it an inverse, or find an inverse. Okay? So now we're going to go through the same process. Go ahead and swap out f of x for y. So this is x equals 4y squared minus 4. And then we're back to solving again. But any questions on why I restricted a domain? Because we wanted to make it a one-to-one, right? Because that's the only way we can come up with an inverse. Okay, so now I'm gonna add 4. So this will just be y squared. Take the square root. When you take the square root of something, okay? Wait. I love when people have those looks because I'm like, what did I do? Hold on, I added 4. I got rid of the 4 again, didn't I? There should still be a 4 there, I'm sorry. I'm looking at that, I was like, yeah, it doesn't match my paper, does it? Okay, divide by 4 first. My apologies. Magic happened. I just magically got rid of a number. Now we take the square root. Now, when you take a square root of a number, you always have a positive or negative component, right? I'm not going to include the negative component because my domain's restricted, huh? So be careful with that. So in this case, and let's just put a note there. So no negative square root because of domain restriction. Okay, that's important. So we're not going to include the negative component. Okay, so now we just what? Write it fancy? Now I can take the square root of 4 to be 2, so I can clean it up a little bit there and reduce it. And that, my friends, is inverses. Well, one-to-ones, but inverses as well. Any final questions? Okay, you guys are awesome. All right, I'm gonna go ahead and pass